In this video, we'll be going over question 4 from the discussion 2A, Physics 103 sheet. So starting off with question 4, we have the oldest word problem in human history. Train 1 leaves Sparta at a speed of 50 kilometers an hour and it's heading towards Athens, which is 150 kilometers away. Train 2 leaves Athens at exactly the same time, heading for Sparta at a speed of 75 kilometers an hour. So part A says to draw a picture of the situation. At the moment each train is leaving its station, choose a point on the tracks where x equals 0 and note the positive x direction. Specify the initial location of each train. So I think this part here is important because we're going to be representing the train's motion with vectors. And vectors have both a magnitude and a direction. So that means that if I choose this point here as 0 on my coordinate plane, I could say any motion to the right of that is positive and any motion to the left of that is negative. I could have also arbitrarily said any motion to the right is negative and to the left is positive, but this is the coordinate plane that I'm choosing for this question. I'm also going to say that this represents Athens, and all the way on the other end, let's get the green color, all the way on the other end represents Sparta. What's that mean? In between the two cities, we know is 150 kilometers. We also know the train that's leaving Athens is heading towards Sparta at a speed of 75 kilometers an hour. So we're going to represent that as a vector. So there's our 75 kilometers an hour, and it's heading to the right, which we specified is in the positive direction. We can do that same thing for Sparta, or the train from Sparta heading towards Athens at a velocity or speed of 50 kilometers an hour to the left. So we have to throw a negative sign onto that speed. So now that we have our picture, part B says use this information from the picture and write down equations for the position of each train. So let's say that x1 is corresponding to the Athens train, x2 is corresponding to the Sparta train. Referencing our position equation here, this is essentially saying that at a given position and a given starting location, and after a certain amount of time has elapsed, if you're traveling at a constant velocity, you will have a new position, and that's what x is. And you can see the equation review video to get caught up on that. So applying that equation, let me zoom out so it stays in frame, we could say that x1, which is the Athens train, is equal to the initial position of that train times the velocity times time, and we could do the same thing for the Sparta train, multiplied by time. So let's look at part C. When the two trains meet, which of the variables in these equations have the same value? Well, we know that they both take off at the same time. It says train 2 leaves for Athens at exactly the same time that the other one takes off. So if they take off at the same time and they meet or they cross paths on the track, we could assume that the same amount of time has elapsed. So that's our first variable. Additionally, if you and someone are in a hallway and you both start moving towards each other at the same time, and then you cross paths for an instantaneous second, you guys have the same position in respect to that hallway. So let's say that this is the crossing point for both of these trains. This is the same position along this x-coordinate plane, which is 150 kilometers long. So now solve each equation for one of the variables we identified in C and set the two resulting equations equal to one another. That essentially means, well, we know, for example, that time is equal in both of these instances, and we know at some point position will be equal in both of these instances. So what if we set x1, or the final position of the train, equal to x2? Because if this was a coordinate plane where this is 0 meters and this is 150 meters, because it's 150 kilometers in length, sorry, let me change that to kilometers and this to kilometers, we know that they're going to have a meeting spot that has the same value in kilometers. And we could arbitrarily say it's like 75 meters or something like that. So therefore, knowing that they have the same final position, we could set x1 and x2 equal to each other. So that's what we mean by the position is the same. So if x1 and x2 eventually equal each other, that means we could say that the equation that's in the blue equals the equation in the green. So let's fill that in. Equals 2 plus v2 times time. Okay, so now we have an equation to work off of. Let's see if we can plug in any variables. So the initial position for the Athens train, let's reference our x-coordinate and say that it is 0 kilometers. So we could plug in 0, and it has a velocity of 75 kilometers an hour in the positive direction, or moving to the right. And we don't know how much time has elapsed when they end up meeting each other at the spot. So then that is equivalent to the starting position of the Sparta train, which we said, if that's 0 for Athens, then this one has to be 150, since we put the two cities on the endpoints of this 150 kilometer line. So we'd say the starting position here is 150 kilometers. Let me just add in the units really quick. So we know that's kilometers per hour, it's a velocity. That's kilometers, the starting position, 150 kilometers, plus the velocity, and here is negative 50 kilometers an hour. And that's because it's heading to the left, as well as the time. So again, the time here is equivalent to the time here. So let's go ahead and simplify this expression and see what we come up with. So we're really just left with 75t equals 150 minus 50t. So let's bring that out here and keep working. So if we add 50t to both sides, we now have 135t equal to 150. Now, doing a simple rearrangement, we can solve for time. Let me just pull out my calculator quick. And, oh, made a mistake here. This is 125. My bad. So then we can take 125 and divide both sides, and we get time is equal to 1.2. And what would our unit be? Well, we're working in kilometers per hour. So 1.2 hours. We'll keep that in mind. So now what we can do with this equation is take this time and plug it back into either this equation or this equation, and then end up solving for the final position, which is also the same. So I'm just going to look at the equation from train 2 and do just that. So let's rewrite the equation for train 2 over here, which is simply said x2 is equal to x naught sub 2 plus v2 times time. So let's fill this in. The starting position for train 2, we said, was 150 kilometers. It started at the tail end of that coordinate system. So x2 equals 150 kilometers plus the velocity, which is negative, heading to the left, 50 kilometers an hour, multiplied by our newly found time variable of 1.2 hours. All right, so let's simplify that down a little bit. So the final position of train 2, which is also the final position of train 1, is 150 minus, and then I'll do 50 times 1.2. Let's see what we get here. 1.2, and that gives us 50 minus 60, which is equivalent to 90 kilometers. So what does that mean? 90 kilometers represents the point on the x-axis that the trains meet. So now we know, we arbitrarily said, hey, maybe it's like 75 kilometers. We know now this is 90 kilometers. Well, what does that mean? That means that this Sparta train moved a total of 60 meters to go from 150 to 90, and this Athens train moved a total of 90 meters because it started at 0 and got all the way to 90. Now, does this make sense? And the answer is yes, definitely, because the Athens train is moving faster, 75 kilometers an hour compared to 50 kilometers an hour. So if there's a meet me halfway thing going on, the Athens train is going to do or move a greater distance before they end up meeting. It won't be exactly at halfway because the velocities are different. So we essentially did part E by solving for the remaining position, which we found to be 90 meters. So now we can fill this in. When and where do the two trains meet? They meet after 1.2 hours. Well, what's the distance from Sparta? We know that was a 60-meter difference. 60 meters, and the distance from Athens, we said, was 90 meters. And I am not familiar with the tortoise and hare question from lecture, but we could assume that there is going to be, anytime that two entities meet, we know that their position has to be the same. We can take that same position, or that the equation associated with two positions, let's say, we can take two equations, set them equal to each other, and then solve for the second missing variable as we did in this equation. What do we have here? Draw the plots of the positions of both trains as a function of time. So as a function of time, position as a function of time. So it's an x in respect to t type of a graph, which means that on the x-axis we would have time, and the y-axis we have the position of the train. Now, we had this picture up here, essentially, and I'll draw it off to the side, a straight line that was 150 kilometers in length, and we essentially said that this point on the far end is 0, that point's 150. We're essentially going to flip that vertically, since this now, the y-axis is position, and say that this top point here is 150 kilometers, and the starting point for position is 0 kilometers. So if we take, let me make sure I get my colors right. We said Athens was blue, Sparta was green. So the Athens train started at 0 kilometers, and it moved at a velocity of 75 kilometers an hour. So the velocity, we know, is a function of time. So velocity is equal to, in units are kilometers an hour. So we could think of distance as in kilometers and time as in hours, which means anytime you have a velocity, you can represent that as a slope, where you have rise over run, rise being kilometers, and then run being hours. So the greater the slope, the faster the velocity, because you're rising faster in a given amount of time. So we could say that this slope here represents the path of the Sparta train. Now, if we were to graph the path of the train from Athens, it's moving at 50 kilometers in the opposite direction. So it's actually starting at the 150, and it's moving at a negative slope, because we said that the velocity was negative 50 kilometers an hour. So not only is the slope negative, but it's actually less steep than the steepness of the positive Sparta slope, because the magnitude of this vector isn't as great. It's only 50. So we're not going to get this exact, but we're going to draw a negative slope at a little bit shallower of a decline. So let's say something like this, and we know eventually, they keep going on their way. Now what we see on the graph is the actual meeting spot of 90 kilometers, and this might not exactly be drawn to scale. And we know that they both meet at the same time, which is what this brown line represents, the same time on the x-axis. So that's a visual way to represent what we just depicted by using the equations. Now, how can we identify the time and the position? Well, the position is where the y values are equal. So let me clean this up a little bit. If we know that our x-axis represents position, then we want to see, well, where do the y-axis represents position. We want to see where the two y values meet. And in terms of time, we want to see where the two x values meet. So that is at this spot in time and this position, which we found was 1.2 hours and 90 kilometers respectively.